All right, good morning, everyone. Today we're going to talk a little bit about computer vision, robots, and mobile gaming. My name is Pawel Szymczyko, and you can learn how to pronounce my name pretty much by just reading the emoji up there, Pawel Szymczyko. It's going to be close enough. And you can tweet stuff at me using my Twitter handle, @Machanai. That's like the word make plus the letters NAI. So, as Jane mentioned, I'm from Las Vegas, Nevada, and I have a lot of makery type hobbies. I'm into robots, 3D printing, electronics, things like that. I work at a small Vegas startup called Wedgies.com, which is a fun name. We do online polling, so it's the wedge of a pie chart, really. Has anyone ever played this game or knows what it is? Show of hands. Awesome. For those of you who don't know, it's called Crossy Road, and it's pretty much endless Frogger. We played this in the office a lot for a while. One of the cool features of this game is that it has a lot of unlockable characters. And much like Pokémon, one of our challenges is just collect as many of them as we can, hopefully all, but nobody's collected them all yet. Some of the characters you can unlock with in-game kind of feats, but others you have to unlock using either in-game coin or actual coin, which can get expensive. You can pick up coins along the road, like a couple at a time, but the real way to earn a lot of coins, because it's a free-to-play game, is by watching advertising, which is kind of boring and tedious. Throughout my cursory knowledge of robotics, I knew that robots are specifically well-suited for tasks that are either too dangerous, too precise, or too tedious for human beings to do. So I decided that obviously the solution to all my problems was a robot. And this is a story of cobbling together such a machine and a program and all the fun yak shaves that came along with it as well. And side note, even though Pokemon Go wasn't out when I started on this, I noted that a lot of the Pokemon Go players have also come up with interesting ways of automating the process of hatching Pokemon eggs like this here, which is pretty cool. One of the main problems with interacting with mobile games is that mobile games are often suited towards human interaction, gestures like swipes and taps, and things that are hard to do for robots and machines that don't have like sausage fingers normally. Luckily, this problem was fairly easily solved already for us, and it was open source. This project is called Tapsterbot. It's a robot designed by a cool guy named Jason Huggins, who designed it. He's actually one of the co-founders of Sauce Labs, so I guess we have Sauce Labs, one more thing to thank Sauce Labs for. He designed it for basically mobile testing and driving telephones and tablets. It's all open source. It's on GitHub. You can get to it through that tapster.io link. And if you have access to a 3D printer, you can print out most of the parts for this robot. If you don't have access to a 3D printer, look up your local hackerspace, and I'm sure they can help you get it sorted out. Tapster is what's called a delta robot. It's a type of robot called like a Cartesian device. Basically, the goal is to move the end effector, kind of business end, the stylus in this case, to certain spaces on the X, Y, and Z coordinate system, like Cartesian coordinates. Sort of a more common type of Cartesian device is seen on these sort of traditional 3D printers like MakerBots and stuff. But those are generally kind of complicated to build. They have a lot of specialized parts like pulleys and screw drives and linear bearings and belts, timing belts, things like that. So they're complicated to build, but they're fairly easy to control because each motor only controls one axis. You turn the x-axis motor, and the stylus moves to the side. So it's pretty easy. Delta robots, on the other hand, are relatively simple to build because they're just made out of motors and arms and joints, but they're relatively difficult to control because rather than one motor being responsible for one axis at a time, all of the three motors work in collaboration to position the end effector in a specific place. And you have to do a little bit of math to get the position right. It's a branch of math called Kinematics, and you have to do an inverse kinematics equation to figure out where the stylus is going to end up at certain angles of the motor. These are the basic parts of a Delta robot, and the thing to take away from this is the motors up top are connected to the upper arms, which move between 0 and 90 degrees, so they make kind of half circles. And the circled points there are universal joints that are kind of like ball and socket joints, like your shoulder, and they can move in 360 degrees, so they can make a spherical shape. And this is sort of like the basis of this inverse kinematics equation for deltas. You have the circle up top moved by the regular joints on the motors, and then the sphere formed by the universal joints. So you have 3 spheres that you can move anywhere along the YZ axis at 60-degree intervals. And when you figure out where the spheres intersect, that is where your end effector should probably be. And it depends on things like the precision of the motors and stuff, but that's the basis of it. It's a really long and confusing equation. So Jason's Tapsterbot design actually came with kind of a simple JavaScript implementation to control it that was adapted from this forum post on Trossen robotics. And as far as I can tell, like all of the knowledge about how Delta robots work came from this one post on Trossen, where some guy took this Swiss white paper, the patent, and wrote it up into a C source code example in this forum. And that was pretty good, but it wasn't something that I could drop into my program because it wasn't really a module. So I ended up taking that and adapting it. I fixed up a few of the equations and created a forward kinematics equation for adjusting precision. I added a queuing system so the robot could perform sequential tasks and wait for the previous task to finish before it does the next one. Some tap and draw methods that just make it easier to control. And I put it up on NPM as J5 Delta, actually just last night, finally. Took a little while. And it supports other types of deltas depending on the configurations you can pass in. The usage example's up there in the screenshot. Hopefully you can see it's not terribly intimidating. You just run the tap method and tell it where to go, or the draw, same kind of thing. Both of the programs were built on top of Johnny 5, which is an excellent library for controlling hardware via JavaScript. Comes from Rick Waldron and crew, so if you haven't checked it out, please check it out. Makes things a lot easier. Next thing we need to solve is well, we have a robot that can now poke and swipe at stuff, kind of blindly, but we need the ability to see what we're poking at. So it should be okay. So webcams are pretty ubiquitous. They're everywhere. I had a bunch of these, which seemed like pretty decent webcams left over from a previous project. The problem was that the majority of webcams that you get for your computer are made for like teleconferencing, and so you move your head and it autofocuses on your head. And they all have autofocus seemingly turned on, which is, again, cool for teleconferencing, but when you have a webcam pointed at a phone and then a stylus comes into view and out, it will constantly keep refocusing between the screen and the stylus, and it'll get really rapidly confused. So I Googled around, and I found this one on Amazon. I think it's a C920 Logitech that claimed to be a manual focus webcam, which is cool, but it doesn't actually have any manual controls like you'd expect on like an SLR. It doesn't have like auto manual or a zoom nozzle, lens thingy. I don't know what you call them. Not a camera person. What it did have is this software control panel for turning it on and off and adjusting some of the other settings, and I thought, that's cool, like I can just live with that and adjust it. But it didn't actually have a memory, so every time I would restart, I'd have to adjust all the settings again, and it got quickly annoying. And so maybe like the first yak shave was like, okay, I can probably reverse engineer this. Let's look into how hard it is. I found this tutorial on Adafruit about reverse engineering USB devices, and it had to connect, and it was looking all really good until it got to the part where it was like, and just take your hardware USB analyzer and hook it up. And I was like, oh, that costs a lot of money. I don't have one of those. I doubled back and I was like, okay, maybe that's not the right path. I Googled some more. I found a project called Video for Linux that does a lot of like webcam and video device control stuff under Linux. Read through the source a little bit. I found out about something called USB Video Class, or UVC, which is a standard that a lot of modern webcams, USB video devices use in order to provide like a common control interface. And it turns out that the USB Implementers Forum, which is kind of like the standards organization for USB, put out a white paper and data sheet about what all of these things do, and then I found an Objective-C example that kind of demystified it further. So I spent a couple of nights writing this package called UVC Control that provides sort of a node interface to controlling your, I guess, webcam controls. So things like the autofocus and also auto white balance and brightness were super handy as well. So now we have a clear image, but we still need to interpret what's going on the screen. And OpenCV seems to be kind of the premier package for any kind of computer vision stuff. It was designed to advance computer vision research by combining like all of the most common, most optimal, well-known computer vision algorithms. And it does a lot of stuff as motion tracking and robot vision, gesture recognition, but it's really geared towards people who already have a really solid background in computer vision. And I don't really. It has a lot of documentation, but it's kind of daunting if you, again, don't really know computer vision. So that's a method called hue moments, and it's actually, believe it or not, a moment is a way of like recognizing a certain collection of pixels, where it'll take like the intensities of the pixels and assign it some number value, and then you can identify like a collection of pixels by the numbers, I think, but I don't know. And that all just looks like Elvish runes to me. Not a math major. But I decided to go with it. And OpenCV is a C++ library. So I needed to find a node wrapper, and there's this one out there, Node OpenCV. It didn't have great documentation, it had like maybe the most popular methods documented. And then it turned out that it supported almost everything in OpenCV, it just wasn't documented. And so normally like a wrapper library like this, it's common to be able to refer back to the original library's documentation, which is in C, and you find the method and you go back and you try it out. But the problem with this one was like a lot of the function signatures were pretty different than the original one. So I ended up having to dive into the source code of the wrapper a lot to figure out how some of this stuff worked, and it wasn't the easiest thing to read and figure out. But mainly got it, and I have a mental to-do for myself to go back in and contribute some documentation and things to make this a little bit more accessible. And so the first actual computer vision problem to solve is similar to kind of what you saw in Miriko's talk. Like when the camera is pointed on the side, you don't really know what angle it's at. You want to be able to take that image and put it into like a rectangular orientation and have a certain size, like you're used to have a clear view of the screen. So this is sort of like the view of what the webcam would look like. And then it's a pretty easy task to do in OpenCV. You run what's called a matrix transform that basically just takes the 4 old coordinates and the 4 new coordinates, and it'll just fix it right up for you as long as you have the right methods. So it's pretty easy there. Read the image in, apply the matrix transform, and boom, it's fixed. I spent a lot of time trying to do this automatically by auto-detecting the screen boundaries, and like a lot of time. And then I was like, it's really hard, and it's not super reliable, and it varies on lighting conditions. So I kind of cheated and instead wrote a configuration interface and a jQuery plugin to just drag these 4 corners. And so shortcut. I figured there was enough like hard stuff to do that I didn't have to dwell on this one. So if I can figure out how to make that generic enough, I might put that up somewhere as well. That got me far enough to basically construct kind of this demo app that let me control the phone from the browser. So what it is it's an Express web server that is constantly grabbing images from the webcam and processing them and deskewing them and then streaming them back to the browser using this really old and unpopular format called mJPEG stream, which I'll show you a little bit more about later, but like almost nothing uses anymore. It's like old Web 1 stuff. And then it listens for click and drag events on the client side and communicates them back to the server using socket.io, where Johnny5 and J5 Delta relay those instructions, translate the coordinates, and tell the Delta robot. So what you see here is kind of a video of me clicking on the video feed in the screen and the stylus coming down and poking at it. So it's a pretty cool demo to start off with. This is just shows the basics of grabbing an image off of the webcam using OpenCV, and then I emit 2 events for the raw image, which is just used in the configuration interface, I'll show you later, and then the processed image, which is the rectangular one, and then the mjpeg stream, which is it's something like /processed.mjpeg. It just constantly spits out the mjpeg header and constantly spits out JPEG images one after another with a specific delimiter. So it's pretty simple. So it worked well without having to do any kind of fancy video codec or anything like that. And the next step up from that is to be able to recognize images on the screen. OpenCV has a lot of ways of doing this. Things like the hue moments, which we looked at, things called surf and sift that are pretty complicated, but they're resilient to things like image rotation and skew and things like that. But I figured that since we're already deskewing the images, we know it's a predictable size and rotation. We can use a much simpler one. And so this method is called the template match in OpenCV. And the first thing to do is basically grab a sample area of the image that you want to match on the source, and that's the play button on the right. The code to initiate match looks like that. First argument is the file name of the sample image, which probably should take like a preloaded image, but it takes the file name. And then the second argument is a match method, which probably should be defined as a constant in the library, but it's not currently. It's another mental to do. Just send a pull request for that. And if you're curious what the other types of match methods are, the documentation's right there. It's very helpful in telling you. Or if you're like me, you would just try them all out and find one that works okay and be like, it's good. What the template match method actually does is pretty simple. It just takes the image and drags it across the source image, and then the output of the function is another image that is grayscale, and it's a collection of pixels where the intensity of the pixel between 0 and 1 is the output of the match function. So it's this image that like tells you nothing, but you know the best matches are either going to be a high intensity value or a low one, and it seems kind of arbitrary. Some are high or some are low. You just have to figure out which one it is from the match method. But for the one I was using, it was high. There's a convenience function to grab the minimum and maximum pixel location intensity. You take that and you compare it to the threshold. A threshold value is kind of like an arbitrary thing, like if it's over this, use it. If you don't use a threshold value like that, you will get a match every time because it'll always find like the maximum one, but you'll get a lot of false positives. Like we're trying to match against the play button. You can see it's matching a lot of things that aren't the play button. They just happen to be like close enough. So the threshold's pretty important. Next, we need to add some control logic because if you tell the program to just click on every button we see, it'll be like the bot has no attention span at all and just can't get anything handled. What we need to do is actually just know when it's the right time to click the right buttons. Like there's a process. Click the right buttons at the right time. I didn't try writing this as a bunch of ifs and thens because I knew it would just be a huge mountain of spaghetti. And it was a chance to try out something new. Even though I'd never used one before, I was pretty sure that what I needed was something called a finite state machine. I'm really bad at explaining these, but a finite state machine is kind of like a conceptual model that dictates how something will behave depending on what state it's in. And then you can send inputs into the state machine, and they can trigger transitions between different states. And that defines how it works. What you see up here is a finite state machine map of a coin-operated turnstile. So if you go up to a locked turnstile and you push it, it's not going to do anything. It's going to stay locked. If you put in a coin, it's going to transition the turnstile into the unlocked position, in which time pushing it will open the turnstile, and then it'll lock again. And then similarly, like if you put coins into an open turnstile, it's not going to do anything. It's just going to stay open until you push it to close it. So you can kind of use this to keep the program on track and make sure it's always doing the right things at the right time. There's a really good finite state machine, or sometimes I call them like flying spaghetti machine library implementation. This one's called Machina. It's by Jim Cowart. It has a lot of event hooks and input handlers that are pretty useful. And I'm going to go through, show you basically how you define one of these state machines. So you set an initial state, and you can have some like handler functions, like that found button there. And then you put the states and the inputs that trigger actions. So in our case, that code at the bottom, every time we recognize a button on the screen, we send that input into the state machine. If it happens to be into a state that has a handler for that state, like if we're in title screen and we find a button called cat, it's going to ignore that because it doesn't know what to do in that state. But if we find one that's play, it'll do something, and then we can transition into the next state where hopefully you can handle the cat button if you want to. So taking a look at the states for this game, the first state is the title screen. And on the title screen, basically you just look for this finger button that's kind of tapping the screen and telling like, play the game. You tap anywhere, and then you transition into the playing mode. So on the playing screen, and so this is the kind of the cheating part, it's really hard, probably, to program the robot to play the game intelligently and dodge all the things. It'd be a lot more code than this. So instead, when we enter the state, I set up a timer to basically just tap the screen every 2 seconds, sending my Crossy Road character probably to a death rather quickly under a car or something. And then when we see the play button again, it means that we've died a horrible death and it's time to transition to the game over screen, but not before clearing the interval so we don't keep tapping. And here is the game over state, in which case, oops, we've died. Randomly, you'll get an earn button that pops up. It doesn't pop up every time. If we see that earn button, we should tap the button and go into the watching mode, which will put you into like an ad watching mode. And then if not, then secondarily, we look for the play button and click that instead to start the loop over again back into playing. And here we are watching a commercial. This again is kind of cheating. I haven't played this game. Looks fun. We just wait 25 seconds until the ad is done, and then it pops up when you can get out this little tiny X target. And again, this is cheating because it's the best way to do stuff. It's hard to find the X, so instead of like finding it, tracking it, and clicking on it, it's got a little precision. So if you like don't click on the right spot, it's gonna go into the App Store and try to sell you this app. So I just tap anywhere to go into the App Store. And then you're in the App Store, and you just click in the upper left corner to go back, collect your coins, and then you're done. So it's kind of cheap, but it works, so it's good for me. So demo, it looks like we do have a little bit of time for a live demo. This will be cool, because these always go so well. Let's see what happens if I even have the right. These camera assignments are rather random. My browser disappeared. Okay. Mouse cursor. Oh, is that you right there? Okay. Is that the right input? Okay. This is going to be really hard, but we'll try. Help. Okay. So let's go. I didn't think this through very well. There are, by the way, the link to the slides, link to Tapster, and link to the NPM modules. There is the configure screen. So this is our webcam here. I'm going to bring up my phone, put it on the thing, point it at the thing. Hopefully it's okay. Oh, this is so hard. Okay. Drag this one. No. Come on. Click target. I wish I had been able to do this earlier. Oh, come on. Yeah. The upper left corner is the upper left corner of the screen, so it's a green dot. I just made that so it'd be easier. Come on, green dot. I'm going to hop down here because I can't tell if that's in focus. That's not in focus at all. Okay, I don't know. That's worse. Let me know when it's kind of, it's okay, okay. Here we go. Don't make fun of my apps. Let's see if this works. Is that on Crossy Road, more or less? Uh-oh, wait, it didn't tap. Okay, there we go. All right, and when I hit the play button here, it should open up like a little window here to show the state transitions, and it'll probably blow up from this point, but let's see. Oh, it's not recognizing the buttons. Why are you doing this to me? My bottom corner. I think if I get the focus right, maybe the brightness, the lighting here is funny. We'll know we've succeeded if the finger gets like a little red box around it. All the way down? It'll be horrible because it's all fixed focus. Oh, but it's still not seeing the button. Well, it would in theory do this. Oh, and it's still tapping. Sorry, it's not, well, it's recognizing that button, but it's in the wrong state. So I think that's all I can show you. If you're interested in seeing this, find me in the hallway somewhere. It'll set it up, and I'll be able to show you in a sane way. But yeah, thanks everyone very much.
Woo! All right, thank you so much, Pawel.